you have an effect of operating cell temperature, right, on fuel cells as well as pressure. So here is an example problem from your book. I'm not going to detail it all, but you have basically on the y-axis here, you have the voltage, right? Here's a line that represents the voltage from a fuel cell as a function of operating cell temperature. So as the temperature of the fuel cell increases, the actual voltage you get decreases, as well as the efficiencies here. You have efficiency if you assume the scale to be starting at 100% here, one representing 100% efficiency. You have a lower heating value and the higher heating value efficiency. That also decreases increasing cell temperature. So that is associated with what you would call the potential voltage coming from it, right? What is the theoretical voltage coming from the fuel cell? But like anything, like in photovoltaics, as you draw power, the efficiency decreases. I'm sorry, not the voltage decreases. So as you draw power, the voltage decreases as the current increases, and you get what's called this power curve, where you get an increase in power due to the fact that you have your current increasing for small decreases in voltage. So as you increase your power demand, you're going through certain what we would call losses. So I'm going to go ahead and kind of try to do my best to describe that. The losses to the voltage or in the fuel cell are basically grouped into three categories. You have the activation loss, which is basically the polarization, the activation polarization as a result of the chemical kinetics, right? So you have basically a certain amount of energy you have to overcome in order just for the actual chemical reaction to activate. After that happens, you have ohmic losses, which is just basically the resistance of the polymer, the resistance of the electrolyte and the resistance of the electric load. And then you have concentration losses when you start basically trying to pull more current than the amount of fuel that your supplying can maintain. So what you have here basically is that your actual voltage that you get is going to be that theoretical voltage, right? Again, this is theoretical voltage compensated for temperature and pressure that we have been just going over in the several slides prior to this one. And then what you do is that we subtract these other losses associated with the activation of the reaction minus the ohmic losses, and also subtracting out any concentration losses. Right, so basically, this is how it looks when we pull it all together. This is a graph that looks at cell voltage on the y-axis versus current density on the x-axis. And so you have the reversible voltage, which is what we've been covering up to this point. Right, a certain voltage that this cell can produce when no current is being drawn. This is the theoretical voltage you can get. As you start drawing current, there's going to be a drop in the voltage supplied as you overcome the activation loss. After that point, you have a certain amount of ohmic loss, right? And that's just a linear decline in voltage for increasing current, as a function of E equals IR. And then you have a certain concentration loss. What the concentration loss basically says is that I'm maintaining a certain voltage for increasing current. I'm increasing current, I have a certain amount of voltage supplying, and then suddenly what's happening is that I'm drawing more current than the supply of hydrogen and oxygen can keep up with. And then what happens is just the reaction just dies out, right? Your voltage drops. If you combine it all together, you get this represented curve, which has a zone associated with the activation loss, a zone associated with the ohmic loss, and then a concentration loss at the end when the fuel can't keep up with the reaction, with the needed reaction rate. So here's a graph that kind of illustrates that a little bit more detailed. Again, y-axis is cell voltage, x-axis is current density, and what you have here is you have that theoretical voltage that we were talking about, right? That ideal voltage that we've been calculating. And then you have a region here as you're increasing your current demand, your voltage drops to in this what I would call the activation polarization region. And then as you're drawing more current, you just have a drop in voltage in accordance to Ohm's law. And then there's a zone here that you approach when your current draw is getting high enough demand that your voltage just drops off because the fuel can't keep up. To end this chapter, let's just look at real quick. It's a little bit of I guess of a matching game here. Here on this slide, we have 5 different situations, 5 scenarios. And I want those 5 scenarios, if you guys want to actually pause the video and go ahead and try this on your own, to match these 5 scenarios with these 5 different illustrated graphs. So looking at this, for example, the first one is saying I have a SOSC, which is solid oxide fuel cell, limited by an extremely high electrolyte resistance. Which one of these graphs would represent a fuel cell with a high electrolyte resistance? So what you would do is just basically take number 1 and then go ahead and insert the number of the scenario that corresponds to the graphs here. So if you guys want, you can go ahead and do that. You can pause the video just to illustrate how it works. You would basically, this scenario E here would show a big drop. Like if I have electrolyte resistance, that's Ohm's law saying that the positive ion is having a hard time flowing through the electrolyte because it has a high resistance. So it would have a big, sharp, linear decrease in voltage as a function of increasing density or current density. So why don't you go ahead and do the rest, the other 4 scenarios. You can pause the video, do that, and then come back to the video here to see if you were able to match them up correctly. Okay, so let's go ahead and do this. Second scenario is a fuel cell suffering from a large leak current loss. In that case, that would be represented by B here. You can kind of see, excuse me, a little shift over of the performance curve to the left, representing a current leak. C is a fuel cell severely limited by poor reaction kinetics. That would be represented by a sharp decrease in the that would be represented by a sharp decrease in the activation loss zone. So that would be scenario C. 4 is a fuel cell with an extremely low ohmic resistance. So in that case, you would have very little loss in the ohmic loss region. So this would be 4, basically not much loss in voltage with increasing current as a result of low resistance. And then that would leave the fuel cell that's suffering from reactant starvation would be scenario D, where you would have just a certain amount of current that you're getting at a set voltage, and then that would drop significantly as you have an issue with fuel keeping up with the reaction. Okay, thank you very much. This concludes the end of the chapter on fuel cells.